Hi, my name is Tarun Awala, and this is my Lab 5, Faraday's Law. So, the goal of this lab is to investigate magnetic induction and eddy currents by examining experimental data of a bar magnet falling through an aluminum tube. These observations are then compared with computational models to better understand the system's behavior. So, the model I used was in GrowthScript, and then the system was just a bar magnet and the aluminum tube provided, and the surroundings were just the external environment. So through the experiment, the average time that the magnet took to go through the tube was 1.27 seconds, while the computational model predicts that it's 0.67 seconds. So these are some of the fundamental principles that we use in this lab. First is Beer's-Savart law, which describes how the magnetic field at a specific point is related to a very small segment of current. And then Faraday's law, which is a changing magnetic field through a loop generates a voltage that depends on how quickly the magnetic flux is changing. And then we also use Newton's laws, particularly the second and third law. The second states that the net external force acting on a system is equal to the rate at which its momentum changes over time. And then the third law, which says that whenever one object exerts a force, the other object exerts an equal force in the opposite direction.
Go.
So this is our experiment procedure. As you can see in the video,
Go.
we just drop the bar magnet through the aluminum tube and just
Go.
wait for it to go through the entire way. Some of the assumptions that we made was that air
Go.
resistance was negligible, the bar magnet behaves like a perfect
Go.
magnetic dipole, and the only forces acting on the system are magnetic and
Go.
gravitational. This is the data from the experiment. On the left, we just have some basic metrics that we took regarding the aluminum tube and the properties of the magnets. And on the right, we have the trial data from the actual dropping of the magnet, and the average time was 1.27 or 1.28 seconds in average. Now, this is the computational model, and this is the code that I had. And basically, this simulates the magnetic falling through a tube. And at the top, we define things like gravity and the dimensions of the system. And then we can create the scene with the magnet and a bunch of rings to represent the tube. And inside the loop, the magnet keeps updating its position and velocity over time. And the main part is the force calculation, which is where the magnet inside the tube, and we apply magnetic force that opposes its motion. And outside the tube, it's just gravity. And then finally, we update the motion using the net force and plot the velocity as time goes on, which gives us the shape of the graph that I'm going to be showing in the next slide. So on the left, it just depicts what actually happened during the experiment. And on the right, it gives us the velocity versus time graph. And in the beginning, you can see that the force of gravity was greater than the magnetic force because the magnet wasn't entirely in the aluminum tube when dropping it. And then while inside the tube, the velocity stays constant because there's no acceleration. Both forces cancel out. And then once it starts to come outside, the force of gravity becomes greater than the magnetic force again because it's outside of the tube. And the model predicts that it takes 0.67 seconds for it to go through. So the interpretation. These are just some things that I interpreted from the model, such as what color represents clockwise and counterclockwise, and what represents the currents, and then what happens if the orientation of the magnet is reversed. How does the experimental measured time compare to the actual time, and how does the shape of the velocity versus time graph indicate the forces acting on the magnet? So some of the errors that were involved in this lab were the measurements, such as the stopwatch timing may not have been accurate due to human error, obviously, and then the magnetic dipole moment may have been estimated inaccurately. And then we also have friction. While the magnet was going through the aluminum tube, it could have had slight contact with the walls of the tube, which may have caused friction and an imbalance in forces. And then also air resistance, which was neglected, but it might have had a slight effect on the magnet's motion inside of the tube. So some of the discussion questions. What would happen if the tube's resistivity were nearly zero, and how would that change the magnet's motion? If it were zero, the induced current becomes larger, and this essentially creates a stronger opposing magnetic field, which increases the magnetic braking force and causes the magnet to fall more slowly. And the second question we have is that what would happen if the slots were cut into the tube? And how would this affect the ring current model? So cutting the slots disrupts the current loops in the tube and reduces the number of circulating currents. And this essentially weakens the opposing magnetic field, resulting in a magnetic braking and allowing the magnet to fall faster. Thank you for listening.